So today we're going to be creating graphs of polynomials, and the thing about creating a graph of a polynomial is that oftentimes we can draw more than one graph. So we're going to be given characteristics like the degree, the roots, the leading coefficient, and we're going to try to draw them. Like I said, oftentimes there's more than one way to draw, and if any of you can help me draw one of them, I would greatly appreciate it. Keep in mind that some of the polynomials described might not be possible. If the given characteristics cannot create a polynomial, we're going to write not possible. And note that we have two sets of axes provided, but sometimes we can't draw more than one way. So let's look at what I'm talking about here on this first problem. We've got a third degree polynomial. We have a negative leading coefficient, and we have one real root. So before spring break, what we talked about is one way that we can identify that something has a negative coefficient is the end behavior to the right of the graph. And so the end behavior to the right of the graph, if it's a negative leading coefficient, means that our end behavior is going to be going towards negative infinity. So people in class can see me pointing downward towards the floor. So if we draw a third degree polynomial, the first one that comes to my mind, which probably doesn't come to your mind, is just this cubic. Because probably what people think about when they think about a cubic function, a third degree, which I'm going to put cubic up here, function, is they think of turning points. And if we have a third degree polynomial, that means that we would have, at most, 2 turning points. But the thing that we need to keep in mind is that we need to have a negative leading coefficient. And as I draw that second graph here, we have our root at that point where the graph crosses the x-axis. And notice to the right of our picture that the graph points towards negative infinity, which indicates that we're working with a negative leading coefficient. By the way, there's probably some other ways to draw this picture. It just happens to be one of those ways. As we look at the next problem here, it's a fourth degree. And what do we call a fourth degree polynomial? Oscar? It's quadrant. Just getting some of the vocabulary back. And we've got a positive leading coefficient and 2 real roots. So before I draw, anybody interested in drawing their polynomial? I'll ask again in a minute. So positive leading coefficient, because it's fourth degree, because it's an even function, we're either going to both go to infinity for our ending values, or to negative infinity for our ending values. Because it's positive, they're both going to go to infinity. So as x goes to negative infinity, y goes to infinity. As x goes to positive infinity, y goes to infinity. Our 2 real roots are here and here on our x-axis. And in terms of fourth degree, remember here's a turning point and here's a turning point and there's a turning point. We have fourth degree, we have 3 turning points. Again, is there another graph that you would like to draw? Otherwise, you get my pictures. And they're fine. So another fourth degree polynomial. Notice our end behavior. The graphs are both going towards positive infinity. And we have two real roots. Fifth degree polynomial. What do we call a fifth degree polynomial? It starts with a Q. Yep. 20. Again, don't want you to forget the vocabulary. We have a negative leading coefficient. Again, that means that our graph will go in the negative direction. We have two real roots, and I do something like this. Let me check my work here. 1, 2, 3, 4. And I didn't quite get it, did I? So I don't have two real roots, I only have one. I'll leave the beginning there. And I still don't have it. Second or third time's a charm. Try again. There we go. We have a root here, and we have a root there. When I look to make sure that my polynomial is okay, what I'm looking at are the turning points of the graph. There's a turning point here, 1, I didn't mark it, 1, 2, 3, 4. So it does seem that it can be a fifth degree polynomial. We have the two real roots, and we do have a negative leading coefficient. I was only able to draw one picture, and you saw me struggle at that on this particular problem, but if anybody has another version, I would love to see it. So we'll move on. That's the only one I could draw, so I don't want to make something up. Fourth degree. We've seen fourth degree. What do we call the fourth degree polynomials again? Anybody? Quartet. We have negative leading coefficient. And we're going to have three real roots. Once again, with the even functions, our graphs either go towards positive infinity, both sides, or go towards negative infinity, both sides. So this one, we have to go both towards negative infinity. We need three roots, so we can do something here and here and here. And it's going to end downward. And I don't have much deviation for my second picture. In fact, as I look at my second picture, there's almost no deviation in my second picture. But we could draw, I guess. Be careful. If you're writing in pen, I wouldn't write down yet until I can make sure to... yeah, I don't even think I want to try. But I will throw out to you, is there any picture that you might want to draw as a second option? Pick your color. Okay. I'll get your paper. Thank you. I'm going to put the arrows on there, but otherwise he did a nice job. With the picture. There's the second choice of the core tip. As long as we know the terminology for these types of polynomials, I think that we can draw them. But if we don't know the terminology, then that's what causes the issue. As we look at problem number 5, it's a 6th degree, positive leading coefficient, and we don't have any roots. So when we draw our picture here, we're not going to touch the x-axis. Or something like that. I do need to count my turning points here to make sure. Positive leading coefficient means that our graphs are, at the ends, are both going to go towards infinity, which it does. We have 1, 2, 3, 4, 5 turning points. And honestly, I do not think that there is another way that we can draw this graph. We could move it up a little bit or we could move it down a little bit. But I don't think that there's any other way to draw with the 0 real roots. When we look at number 6, 3rd degree, positive leading coefficient and 0 real roots here. Well, even if we go back to 3rd degree, which by the way is a cubic function, if we go back to example number 1, both times that we drew number 1, we ended up crossing the x-axis. Is there any way that we can draw a graph of a 3rd degree polynomial where we don't cross the x-axis? And there isn't. This is not possible. And let's see, though, if we can draw the last function. And the last one is a 2nd degree function. What do we call a 2nd degree polynomial? Still starts with a Q. There we go. All right. We're only going to cross the x-axis once. We have 1 real root. And we have, again, a positive leading coefficient. When we have our even functions, 2nd degree, 4th degree, 6th degree, they're either going to end, both of them, going towards infinity, or both of the ends going towards negative infinity. Because it's positive, we're both going to go towards positive infinity. And there's our 1 real root.